This is Jack Jackson. We're going to talk about derivatives and, well, characteristics of polynomial functions in general. We saw some of this earlier when we looked at derivatives of cubic functions. Notice that polynomial functions are sums of power functions, so we easily know how to do the derivatives, like we talked about in our last video. But it turns out that because polynomial functions are sums of power functions, every time you do a derivative of each term separately, you're going to be subtracting one from the powers. So the derivative of a polynomial function is always another polynomial function which is 1 degree lower than the original. Now remember, a polynomial of degree n could have at most n linear factors, so it's going to cross the x-axis at most whatever the degree is. Now degree is the highest power. So for example, in this cubic function, it could cross the axis up to 3 times. In this 4th degree polynomial, it could cross the x-axis up to 4 times. And in general, no matter what the power is, that's how many times it could cross that axis at most. Notice then that the derivative is going to be 1 degree smaller. So in this case, a cubic is going to have a derivative which is a quadratic. It could cross the x-axis at most twice, which means that this one could have, the original could have at most 2 extrema. Here the derivative is a cubic that could cross the x-axis at most 3 times, so you're going to get at most 3 extrema here. And there is evenly spaced as you could get, so there's either going to be 2 max and 1 min, or 2 mins and 1 max, or if there's 4 extrema, there'll be 2 max and 2 min. They'll be evenly divided as evenly as you can get it. The second derivative is going to go down one more level. So in this case, well, let's look at the cubic first. The derivative here is a linear function. It has 1 x-intercept, which is going to end up giving you 1 inflection point on the original. Here, the derivative, second derivative has 2 x-intercepts, which means the derivative could have 2 extrema, and the original function has 2 inflection points there and there with the same x values, where the second derivative is 0. So notice that in general then we get the conclusion that first of all these derivatives exist. So these are nice and continuous functions. It's not going to have any sharp corners. They're not going to have any holes in the graph. No vertical asymptotes. They don't have any horizontal asymptotes either. There may be some wiggles, some up and downs, but eventually they kind of settle out. Like this one is all concave up, increasing at the right end, and concave down, concave up, decreasing on the left end. The arrows just kind of keep on going. That's why you kind of put an arrow on there and pretty much kind of know what's going to happen outside of the window. All the interesting stuff is kind of happening in here. What is the interesting stuff? Well, if it's degree n, it could have at most n x-intercepts. It could have at most n minus 1 extrema, and it can have at most n minus 2 inflection points. Sometimes that can go down. For example, y equals x cubed doesn't have any extrema. It only has the 1 inflection point. But at most, if it's degree n, it can have at most n x-intercepts, at most n minus 1 extrema, at most n minus 2 inflection points. In my algebra notes, I talk a lot about this, not in terms of what the derivatives are, but in terms of looking at several examples of polynomial functions, what the end behavior looks like, and this idea of where these max and min and inflection points are, at least in terms of visualizing them. And so I refer you to those notes for some more examples of polynomial functions. You can also use this GeoGebra app to type in your formula here and get the derivatives to work out here. Okay, see you later.